All right, now I'm going to cover reliability and validity. The basic idea is once you establish what variable you're interested in measuring, you need to think about the quality of your measurement approach, and you're going to do this along the axis of reliability and validity. These are related but distinct constructs that are both important to evaluate in assessing the quality of your measurement choice. So once you've made a decision about the variable you're interested in studying, you want to think about the issues of reliability and validity. Reliability is essentially the consistency of the results your measurement provides. Consistency is going to mean different things. You're not going to need to demonstrate all consistency types. It's going to depend on the variable you chose. So there's going to be different reliability types, and you have to evaluate A, which ones are important, and B, actually evaluate whether or not you cleared those bars. Validity is, again, related but distinct, and this is more so about measurement accuracy. So reliability is all about consistency. Validity is a little bit more abstract because it's about accuracy. It's about, does my variable actually measure what I want it to, or am I inadvertently measuring something else that I don't really care about? Again, there's going to be various validity types, and it'll be up to you to think through which types are relevant and whether or not you cleared the bar for actually having the type of validity that's important. So a good measurement choice should ideally yield as much consistency and accuracy as possible in the specific ways that matter to you and matter for your measurement choice. So again, we need to get into the subtypes of reliability and validity to understand what they are so we can know when different types might be relevant. Okay? So again, reliability is about the consistency of the results that your measurement approach provides. So this is going to break down to various subtypes of reliability that again are going to apply to certain variables some of the time. One reliability type is what we call test to retest reliability. This is when you get the same results along multiple administrations of the same test. If you give people a certain survey to complete at time 1, do they get the same or a similar result when you give them the same survey a month later? Not all measurements need necessarily to have test to retest reliability. Some do. If it's a variable that you think should be stable or relatively stable over time, you likely would want test to retest reliability. Let's say you're measuring people on personality. We conceptualize personality as any trait or characteristics people have that remain pretty stable throughout the lifetime. It can fluctuate a little bit, but we think of these traits as semi-stable. If I administer a neuroticism questionnaire, that's a personality characteristic, if I administer a neuroticism questionnaire to my participants at day 1, if they take that same questionnaire 7 days later, are people going to get similar results? If I was to try and do this, and individuals who were reportedly highly neurotic at time 1 were not neurotic at time 2, I likely have a problem with my measurement. I'm likely not actually tapping into neuroticism because that's meant to be kind of stable. Maybe I'm inadvertently measuring something that's not necessarily completely stable over time, like mood. That would be a problem. It's perfectly reasonable for there to be some measures that you don't necessarily look for test to retest reliability. You do want your measures to be accurate, but let's say you're assessing people on their amount of stress. And to do that, you're measuring their level of the stress hormone cortisol. You don't necessarily expect those values to be exactly the same at different testing times. People's cortisol spikes when they're more stressed. So test to retest reliability in that case is maybe just not relevant, and so you don't need to evaluate your test to retest reliability. Inter-rater reliability is going to be specifically relevant when our measurement involves observational data collection. So inter-rater refers to the consistency between multiple coders or observers that are collecting data. So let's say I have 2 research assistants and they're observing participants, and maybe they're making a checklist for how often a participant moves their chair away from another confederate or how often the participant does anything. If I have multiple research assistants who are both coding the same thing, I want them to generally be seeing the same things. I want their ratings to be consistent. Now, maybe the rater, one of them at one time point fails to see something that the other did, or maybe they see something that's not actually there. So maybe there's like a small discrepancy. They're a little bit off. That's likely okay. So we don't need perfect consistency between our coders, particularly if they're coding something that might be a little bit more subjective. But generally, you do want your raters to be pretty consistent. If you have different research assistants who are making the same observation but giving you wildly different results, you have a problem because you don't know what is actually true. So if you have data that relies on coding or observational responses from multiple raters, you need to evaluate inter-rater consistency. If you do have consistency, great. If you don't, you probably need to do things over. Internal reliability is when all the items or questions that belong on a single scale generally agree with one another. Essentially, you want the items that exist within one scale to correlate with one another. If there's a certain question that participants are responding to far different than how they're responding to all the other questions, it's going to ding your internal consistency. The question becomes, is there an item in my scale that doesn't belong? Evaluating internal reliability is often the work that gets done when researchers are creating and publishing new scales from scratch, when they're basically writing their questions from scratch. This process of writing new questions, evaluating their internal consistency, and dropping the items that don't belong, it takes a long time and it's a huge pain in the ass. That's why I always recommend students choose pre-published scales whenever possible, because it is harder than you would think writing your own questions and making sure that they all agree with one another. The basic idea is that, let's say I have my participants respond to 7 questions evaluating their level of self-esteem. I'm likely going to want to create an average self-esteem score for all my participants based on the mean of their answers to those 7 questions. If one of those 7 questions is out of step with all the others, I am left with a sort of bit of confusion as to what that question that doesn't belong was really assessing and whether or not it should actually be incorporated into the average. So to evaluate reliability, one very easy strategy to do this is to visually assess the association between whatever consistency type you're looking for. So in order to do this visually, you can use what we call a scatter plot. A scatter plot is essentially a graphic that depicts data points as pairs of values. So if, let's say, you are interested in the correlation between anxiety and self-esteem, you would have a series of participants who gave you both an anxiety or a self-esteem value. The data point, their position along the x-axis, would tell you where they fall along the first variable, and the placement along the y-axis tells you about their level of the second variable. And by visualizing the scatter plot, you can get a sense whether or not people's scores are going together. So I'm going to show you examples of how this actually works for our different reliability types. So for a test to retest reliability, the consistency you're looking for is consistent results among different administrations of the same test. So our 2 variables are going to be scores on testing time 1 and scores on testing time 2. And we can use this visualization via scatter plot to inspect the strength of our test to retest reliability. So for example, it might look like this. As I mentioned, the scatter plot is where data points represent placement of a certain individual along 2 variables. So as you can see, those data points, where they fall along that x-axis, that one at the bottom that says test, that tells you what score they got at time 1. The placement of the dot along that y-axis going up to down, that says retest, that tells you what score they got on time 2. Essentially, the fact that those dots, those data points, appear to be sloping upward and they appear to take on this sort of coherent linear shape. It sort of looks like they are forming a little bit of a line, not perfectly, but they sort of are trending that way. That tells you that there's a strong positive association between scores that individuals got at testing time 1 and testing time 2. So that's good. This would indicate that there's a decent amount of test to retest reliability. You might be saying to yourself, wait, I see a rogue data point, someone who got 20 at testing time 1 and a 40 at testing time 2, that data point towards the top that you see there. That obviously would be an outlier, and you would probably want to evaluate what happened there. Most of the other data points seem to be telling a story of test to retest consistency, so it is worth asking why there is an outlier there. Maybe that one participant was just really tired or stressed on the first testing day, and their result didn't really reflect their actual performance, and so they performed a lot better at time 2. Certainly, that might be cause for concern that test to retest reliability was not completely met. But overall, by visually eyeballing this scatter plot, you can get the sense that most people have a good amount of test to retest reliability. Inter-rater reliability, you can do the same thing. It's just that the two variables in this case are going to be your responses from coder 1 compared against your responses from coder 2. So you could once again create a scatter plot to visually assess the consistency between your coders. As opposed to the scatter plot showed in the previous slide, you can see that these data points are kind of all over the map. There's no real coherent linear or line-like shape to these data points. They kind of look like a blobby cloud. There might be some positive association there, but it doesn't appear particularly strong. It appears that coder 1 and coder 2 might be giving you pretty inconsistent responses. If you get a result like this, essentially it just gives you an indication that there was not enough inter-rater reliability, and you might want to go back and re-examine what was going on with your coders. You might want to retrain your coders to make sure that they're sort of living in the same universe. The broader point is that it's important to assess the reliabilities that are relevant to your measurement because it gives you an opportunity to identify flaws that might be present in your measurement strategy. Inter-rater reliability can additionally be numerically calculated. It can yield a single numerical value that tells you about the extent of your inter-rater reliability. The easiest way to calculate this IRR, inter-rater reliability value, is to just divide the number of agreements your raters gave you over the total possible number of agreements. So for example, let's say you had 2 raters who are just taking a series of observations at 10 time points. The number of times they agreed, right? They agreed at time 1, they agreed at time 2, time 3, times 4, so on and so forth. The only time they didn't agree and rater 2 marked that they saw something that rater 1 missed was at time 10. So they had 10 opportunities to agree, and they agreed 9 times out of 10. So this is the most basic way to calculate your IRR. If you're wondering if that's a good enough amount of inter-rater reliability, the basic answer is yes. There's no real clean cutoff for what is an appropriate amount of inter-rater reliability, but anything sort of above the 0.8, between 0.8 to 0.9 range, you're okay. And anything above is very, very good. Getting below that 0.8 range, you might be thinking to yourself, is this a subjective assessment? Does it make sense for there to be that much disagreement? So a lot of the times, research that relies on coders to make observational assessments is going to be a little bit more complicated than the example I just showed you, where they basically respond to a yes or no question. So an example of this that I'm going to show you is from some of my own research many years ago at this point, where I was interested in people's experience of unfair versus fair anecdotes in their life. Basically, what I had participants do were write about certain experiences that they had that were either fair or unfair and were either positive or negative. So I was just having participants write a narrative about something that happened in their life. To make sure that participants were doing what they were supposed to do and actually writing about unfair experiences when prompted to do so, is I had coders read all of the narratives and assess the narratives on like a 1 to 5, I think, scale. Basically, two coders sat down and they read all of the same narratives and they assessed just how fair or unfair the narrative actually seemed to them on a 5-point scale. Okay, so what I ended up with was an inter-rater reliability of, you see there, that little squiggly thing? That's an alpha. That alpha equals 0.88. That's my inter-rater reliability. Like I mentioned, if you're above zero point 0.8, you're in a very nice range. There's a high amount of agreement. So even though my coders were able to have their own subjective assessment of the narratives, this strong inter-rater reliability told me that participants were writing about the themes that I wanted them to. People who were asked to write about fair experiences were writing narratives that appeared that way to my coders. So I definitely wanted there to be some amount of inter-rater reliability. It didn't need to be perfect, right? They were able to come to their own decision about how much unfairness was exhibited in the narrative on a 1 to 5 scale. So a little bit of disagreement is fine. But I definitely wanted to make sure that my coders were seeing the same themes when they were reading the same narratives. And this is going to be basically the heart of the lab quiz that we do on reliability. Your example is going to use something very, very much like this to help you start to analyze some Chromebox alphas for inter-rater reliability in SPSS. Okay, so now moving on to our internal reliability. Like I said, a alpha score essentially is a numerical output that tells you about the strength of the relationship between the questions you're looking for consistency on. So for example, this might be your inter-rater reliability, like I just mentioned, where that alpha stands in for the consistency between my two raters. This same value is going to do the same thing when we go to evaluate internal reliability. As I mentioned before, internal reliability has to do with the internal consistency between multiple questions in a single scale. So this is statistically relevant because this is a statistical computation that we'll be doing in SPSS, but it's also conceptual. It basically captures the extent to which a given scale containing a series of questions makes sense together. This is often included when you're doing your descriptive statistical write-up, and it's part of the paper that you would write where you basically go over some of the key characteristics of the measurement scales that you've chosen. So it's important to evaluate the extent to which a scale is internally consistent because that tells you about the quality of the questionnaire. Okay, so in terms of creating a scale, you're going to see when you start looking up questionnaires and surveys on your own, a lot of what we call scale development or validation papers. And you might be wondering what that means. Isn't creating a scale likely just going to be writing up the questions that you think sound good? That's not really good enough. What you would see if you actually read some scale validation papers are a series of what we call psychometric analyses to evaluate the strength of the questions. So one thing that researchers do is they iteratively evaluate the internal consistency of their scale by deleting certain questions one after the other. Essentially, they create all of their questions, and then one at a time, they rerun the reliability analysis, subtracting one question at a time. What this allows them to do is evaluate an overall reliability for all the questions, and taking out one item at a time and rerunning the reliability essentially allows the researchers to identify if there's any single question that is detracting from the overall reliability. This is an example of a screenshot from a paper where the items the researchers created all seemed to be jibing together quite well. As you can see, the overall reliability listed at the top there, that alpha of 0.82, that's their Chromebox alpha for the overall internal reliability. They went through and they reran that Chromebox alpha with each one of those 10 questions deleted from the analysis. And as you can see, all of those Chromebox alpha are pretty similar. What that tells you is that all 10 of these items appear to go together quite well. As you can imagine though, This process just takes a while. This is why it's typically best practice, if possible, to use a pre-published scale, because this is all of the effort that goes into creating good, solid, quality measurements. And only scales that have gone through this process end up getting published. And once the scales do get published in a paper, in a journal, the idea is that it's then available for other researchers to use freely. Okay? So don't create your own questions if you don't have to, because this is annoying. All right, so that's all your reliability types. Now moving on to our validity types. So as opposed to reliability that assesses consistency, validity is more so about accuracy. So this is more so, does my measurement actually assess what I want it to? The idea is that you might have a measurement that's consistent time and time again, but if it's not actually tapping into what you want it to, you have to ask yourself sort of, what are you doing here? So how do you actually assess the accuracy of your measurement type? Well, you have to start somewhere. You can start with what we call face validity. So this is your most surface level assessment. Do the questions in my scale seem to make sense to assess what I want them to? Let's take that subjective well-being scale that I showed you a little while ago. The questions in the subjective well-being scale are things like, are you a happy person? You might think to yourself, yeah, part of well-being is happiness. That makes sense to me. Obviously, this being the most surface level assessment, it doesn't quite go deep enough, but it's a good place to start. Right? When researchers are creating new scales, they have to start somewhere, so they start with face validity. It's just a question of asking yourself, what kind of questions do I think can help me tap into the construct I'm interested in? And this gives you a place to start. From there, you can do more psychometric assessments to delete items that don't make sense or create new items, but you have to start somewhere with your face validity. Content validity is going to be when you assess whether or not your measurement adequately captures the entirety or breadth of your construct of interest. This will be particularly important when you're dealing with constructs that might be very multifaceted or have lots of different factors that go into that construct. My example of this is always depression. Depression is a pretty multifaceted construct. There's lots of different various symptoms that go into depression. One feature of depression is sadness. So if I was to ask a series of questions about sadness to my participants, I have not met the content validity bar. The idea is that I'm only measuring sadness, but depression and sadness are not the same thing. Being sad is part of being depressed, but there's so much else that goes into it. There's the anxiety and the rumination. There's the feelings of worthlessness. There's the physical disturbances, sleep disturbances, appetite disturbances. There's the cognitive disturbances. If I'm only asking about sadness, I am losing the breadth of the construct of depression. So a scale, for example, like the Beck Depression Inventory, more so does meet that bar for content validity, because if you look at the items for the BDI, you'll notice that all types of questions related to the breadth of the construct of depression are present. It asks about sadness, it asks about anhedonia, it asks about sleep disturbance. The BDI really more so does meet the bar for content validity. To evaluate content validity, the process is to ask yourself, what is the breadth of my construct? Do I have questions that cover all of the facets of my construct of interest, or is there something missing? The next two types of validity are going to have subtypes within them. I'm going to recommend right now to pay more attention to the subtypes because they are far more intuitively named than the broader types. But let's jump into them. Criterion validity is validity where you assess whether or not your measurement of choice is related to some outcome, either now or later. So remembering that criterion is about assessing outcomes, that might be a little bit hard to remember. What's a little bit easier to remember are the subtypes that break it down. So concurrent validity is whether or not your measure predicts some performance right now. Right? So that's what concurrent means. It means happening at the same time point or concurrently. Predictive is again more intuitively named. Predictive validity is when your measure might predict future performance. So, to understand what these two subtypes mean, let's take something like a standardized test. Standardized tests are typically required for admission into college or graduate school because the idea is that they've displayed both some concurrent validity and some predictive validity. The idea is that, let's say you perform quite well at the quantitative section of the GRE, the exam to get into graduate school. The idea is that if you sit someone down to take the quant GRE, it's likely going to predict their performance on a math exam that they would take right after the quant GRE. So basically a concurrent assessment about whether or not the quant GRE assesses ability to perform at another math exam. So that would be evaluating the concurrent validity of a variable like performance on the quant GRE. Predictive validity is especially relevant to standardized tests because this is really what most colleges and grad programs are banking on standardized tests being able to do. The idea is that performance on a standardized test is pretty reliably associated with future outcomes. The idea is that performing well on the ACT or the SAT is predictive of a higher college GPA. Now, standardized tests are not perfect. Not everyone that doesn't do well at a standardized test performs poorly at college, and some people who perform well on the SAT don't do well in college. Operation Varsity Blues, I'm looking at you. The idea, though, is that colleges and graduate school programs have evaluated that there's enough predictive validity to standardized tests that they're a decent metric to try and capture future performance. So again, criterion validity breaks down to concurrent versus predictive. It's generally about assessing outcomes, but those are outcomes that are either measured basically at the same time as the assessment or further into the future. Okay, construct validity. Construct validity is making sure that our measurement captures what we want it to by mapping it against other variables. So this is similar to criterion, but it's not so much about predicting an outcome versus just mapping your measure against some other variable that's maybe not necessarily related. So again, construct breaks down to slightly more intuitively named subtypes. Convergent validity is when your measure is associated with a related variable that you think it should be. Let's take depression, for example. Depression is thought to be associated with the distinct variable of self-esteem. You wouldn't necessarily think of self-esteem as an outcome of depression, but you definitely would think of it as a variable that should be associated with it. Depression and self-esteem are not the same thing, but they're definitely related. So if you were to take participants' measurement on the BDI and take their measurement on a self-esteem scale, the idea is that you would check whether or not those scores were associated with one another, because the BDI should pretty reliably be associated with self-esteem. If you're creating new depression questions and you find that scores on your new depression inventory are not associated with self-esteem, the idea is maybe you should go back and make sure that you have good quality questions. Divergent validity, on the other hand, is the flip side to convergent, whereby your measurement should not be associated with variables that it should not be related to. So to take the same example of depression, you might, in the process of creating your new depression inventory, maybe take an assessment of, let's say, intelligence. Depression and intelligence should not be associated with one another. They are completely distinct variables, and there's no good reason for them to end up being related in your data set. So this would be a strategy whereby you seek to assess your variable against something it shouldn't be related to, and you make sure that it's unrelated. So these are a lot of different reliability types and a lot of different validity types. And you might be thinking to yourself, would it be possible for me to have good, strong measurement that clears all of these bars? The answer is that you really cannot achieve perfect measurement because there's no such thing as perfection. There's going to be a downside to whatever measurement choice you have. You really can't achieve every kind of validity, and there would be no way to achieve every kind of validity to a bar of perfection. What you should do, though, is you should assess whether or not any particular kind of validity is most important to you. And you want to make sure to really closely eyeball any assessments you've made for that validity type. And if you don't clear the bar you set for yourself, you need to reevaluate whether or not you should choose a distinct measurement type. Additionally, it's important to think about reliability versus validity. They both are important to evaluate measurement effectiveness. One distinction is that reliability additionally has this statistical component associated with it, so that makes it a little bit distinct. But they both are important to look into. One final point that I'll make on validity versus reliability is that reliability doesn't tell you anything about validity. Please do not confuse the two because they assess two very different components of measurement effectiveness. But having a measurement that's reliable tells you nothing about the validity. A measurement can be consistent and give you consistent results, but that does not mean it's accurate. The classic example to demonstrate this would be your polygraph test, your lie detector machine. Polygraph tests are very reliable in that they very consistently give you accurate information that doesn't necessarily actually give you the information you want it to. By that I mean polygraph tests essentially measure your physiological arousal, and they're very good at that. They measure your heart rate, they measure the conductivity of your palms, essentially the amount that your palms are sweaty. The idea is that physiological arousal is associated with lying. Thus, the polygraph assesses physiological arousal, and as such, it tells you whether or not someone is lying. This is logically pretty flawed because we become physiologically aroused in all kinds of circumstances where we're not lying. Maybe we become nervous when we're being interrogated. That would render the polygraph pretty useless. So even though it's reliably assessing your skin conductivity, it's not with any validity actually assessing the extent to which you're lying. So polygraphs are a great example for demonstrating that reliability does not equal validity. So don't confuse the two. Just because a measure is reliable does not mean it is valid. You need to evaluate them separately, and one does not tell you about the other. Okay, so I'm going to end this section right here and pick back up with the last chunk for this lecture on research claims.